to another series of the protein functionality, and today we'll be looking at the different roles that proteins can play in the food system. So most of the times when you hear about proteins, number one, maybe the thing that comes to your mind is about the proteins that you consume and what they do in your body. But in this episode, I'm not going to be looking at proteins in the body. However, I'll be looking at proteins and the role that they play within food processing. So we'll look at what is it that you can use those proteins rather than when you consume them and they have an impact on your body, the physiological impact on your body. However, in this case, we'll be looking at where you use those proteins outside the body, and that is going to be in food processing. So what are functional properties of proteins? I think a couple of months ago I've talked about different functional properties of proteins in some of the episodes. So if you missed any of those videos, feel free to check them out. I'm gonna link them below this in the comments below, and you can still click on to be able to go back into those fundamental functional properties of proteins. But this is just basically when you talk about the functions of proteins in food processing, is looking at the physical and the chemical properties of proteins. Why are they important? It's because they influence the protein behavior in food systems, and this is important during things like the preparation, the processing, the storage, and of course the consumption of the food. They also contribute to the quality as well as how you perceive the food, so that's the organoleptic attributes of food and the food systems. And that is why it's important for someone to be able to understand or to be able to correlate or look at the functional properties of proteins. One of the other things that is important for me to note or to mention at this moment is that many of the food products that we have, actually they owe their function to food proteins. Because for example, if you have a yogurt or you have cheese or whatever, you cannot have cheese without having the proteins in there, which are the caseins. And the way the caseins, for example, you can't have a yogurt without having the milk proteins, etc. Why do we need to understand the functional properties of proteins? You'll be asking yourself, oh, well, why do I bother to do this? And I'm looking at it from a food science, food processing point of view. Number one, you need to be able to understand that because of it enables you be able to develop and improve existing products. So we know the product development or product design is something that is ongoing. And of course, I've always loved to talk about the increase in the global population. That means that the food industry needs to really diversify and look at opportunities of coming up with newer sources of proteins. And so we'll end up developing new products. But also, if you want to improve existing products, you need to start by understanding the role that the protein will play in those products. And of course, I'm a great believer or strong advocate of exchangeability of proteins, where you can be able to exchange proteins in one system or the other, so that at the end of the day, instead of, let's say, using animal proteins, which we know they are very heavy on the environment, you can actually exchange and use the plant protein counterparts. And this can only be possible if you understand a given functional characteristics or functional property of the protein within that system or within that matrix, so that when you're thinking or planning of changing that protein, you need to understand, if I've got, let's say, gelatin, which is an animal protein, and I choose to change it or substitute it with a pea protein, are they going to be able to function equally, or is it going to be different, just mainly sometimes because of the inherent differences between the animals and the plant proteins? It's also important for you to understand the functional properties of proteins, because that can help you, particularly when it comes to new protein ingredients. I've already mentioned a bit of exchangeability, but then of course we are also tasked per se with being able to understand particularly what are the new functional ingredients out there. And of course, if you're looking at a new protein ingredient to meet up with all the increase in demand, and of course in the population sizes, and of course just trying to catch up with people's eating habits and dietary behavior, then you need to understand the functional properties of those proteins. I'm going to just give a quick highlight of some of the examples of proteins, protein functional properties in different food systems. So when I'm looking at these different food systems, I'll give examples of those food systems and the functional properties. One of it is solubility. Again, as I said, I've talked about these functional properties before. So again, I'm going to link the video below so that you can go back to it and listen to it if you missed it. But things like solubility, you want to understand how you can disperse the protein in, let's say, a given matrix. It could be water, for example. And in this case, you have examples of things like beverages, protein concentrates, and isolates. So for example, you want to go to the gym in the morning or after morning run, and you just want to have a quick protein shake. It depends highly on the solubility to be able to have that. And then there is the water binding and water holding ability. I will talk a little bit about that today in this video recording. And of course, this is important in things like muscle foods, cheese, yogurt. You want to be able to have some level of water binding or water holding ability so that you are not ending up with a product that is out of spec. Then there is gelation. I've explained a little bit about gelation again in another video, but if you missed it, I'm going to link it below. But this is mostly important in things like muscle foods, yogurt, gelatin, baked food, etc. And then there is emulsification, which is important, where you're just trying to mix water and oil in different interfaces and understanding how you can actually have the protein sitting on the interface between the water and the oil. And that provides a good way of these two guys loving each other, because generally we know the water and oil never mix. And this is important in things like salad dressings, mayo, etc. Because if you do not have that protein sitting on those interfaces, then it becomes much more difficult, because your product is going to separate into those immiscible phases, and that can impact the consumer's behavior or ability to appreciate what you're making. Then there is, of course, the foaming, which is important in things like cappuccino foams, meringues, marshmallows, etc. They are all where you're having an interaction between air and water, and the protein can actually work so nicely by again coating itself in the interfaces. So I'm going to talk a little bit today more into details on the water binding or water holding ability or capacity. I know sometimes people constantly confuse these two terms. It's not necessarily a substitute of the other. They don't necessarily mean the same thing. And hopefully, as we come towards the end of today's session, you'll be able to see the differences between these two terms. So when you're thinking about water binding, it's just the ability of foods to take up or hold water. And of course, this is important when you're looking at food processing, etc., because at the end of the day, it can impact on the behavior of the product that you're producing. Just something that you need to understand is that if you have more water, it means you have a higher product yield. And of course, the food industry is not a charity. They are there to make some money. So that means there's going to be a higher financial benefit. And of course, if you've got less water, it means the less yield. And that can have an implication on the company's or the business's financial benefits. When you're looking at also the product quality, things like juiciness can actually be affected depending on how the product binds to water. Because if it binds to the water and it cannot exude the water out of its matrix, then of course it can have an impact on the juiciness of it. So how do you, of course, when you're looking at water holding capacity, so water holding capacity, just looking at the ability of a material to retain its own water under external forces such as compression or centrifugation. So the typical way in which you will determine the water holding capacity, you've seen here, for example, you have something that you want to look at, the water holding capacity of that product. You weigh the product initially, and then you will go through the process of centrifugation or compression, and then after that you look at the changes in the weights. You have the initial weight and the new weight divided by the initial weight multiplied by 100%. That should actually give you the percent water holding capacity of the product. So again, it's just the ability of a material to retain its own water when you're trying to compress it. And of course, when it comes to water binding, it's the difference comes in because it's going to be looking at the material's ability to bind extra water that is added to the product. So retaining the water under compression is water holding, but binding is binding, as the name suggests. So I'm going to just talk a little bit about different factors that can impact the water binding capacity of protein samples. So for example, if you are a food science student and you're watching this video, listening to it, you'll understand maybe it could be an exam question that you can be asked to explain the different factors that influence the water binding capacity or water holding capacity of protein samples. Or maybe if you are in food processing, you might want to understand what are these different factors that impact the water binding or holding capacity of your samples, of protein samples, so that you can be able to understand the characteristics of your samples, and that can play some important role when it comes to product development. Number one is the type of protein. So if you've got a protein that is more hydrophobic, it just means it doesn't love water. That means that it's of course going to uptake or bind less water. But if it's hydrophilic, that's it loves water, then it's going to be able to bind or uptake more water. I'm going to talk a little bit about different types of protein in another clip of a video, so I'm not going to go so much into details in this clip because I just want to talk about some of the factors that influence the water holding or binding capacity. The other thing is the protein concentration. So if you've got, let's say, a more concentrated protein system, then you end up uptaking more water. So try to imagine or visualize with me. You want to prepare your shake in the morning. You've come back from a run, like I love to run. I mentioned there's a couple of videos. Or you are gone to the gym and you want to have a protein shake. If you take your protein powder, whey, pea, wherever, you put it into a container or the shaker. So if you end up with a high concentration without having enough water, the water was not going to be able to uptake. And if it's not going to be able to uptake, you're not also going to have solubilization. You end up just with a product that is actually mashed together, clamped together. And that means the more concentration you have, the more water uptake. And if you have a less concentration, the less water uptake. The other thing is protein denaturation. I think I've talked about protein denaturation in other couple of videos, but it is where you are able to begin to have that unfolding of the protein structure, because generally the proteins in nature, for example, are usually folded. So when you start to unfold those proteins, which can be as a result of things like temperature, you go beyond the denaturation temperature, the protein begins to unfold, and that actually exposes those hydrophobic patches that usually are hiding within the protein. So what happens is that, for example, when you heat up proteins at a good enough concentration, you go beyond the denaturation temperature, the protein will unfold and it results into the formation of a gel. And of course, I've mentioned this in another different clip of a video, that a gel is just a matrix that is able to entrap water in it. So if you've got some matrix or a 3D dimensional or three-dimensional network that is able to entrap water, to hold water in it, once once you have that denatured protein, you form a gel, depending on, again, on the different types of gels that you can form. I'll talk a little bit about them later, that can impact the ability to hold or to bind. So let me show an example here where you have the water binding microliter per milligram of protein, and you've got 3 different proteins. So you've got soy protein suspensions, you've got caseinates, which of course is from animal, and then you've got whey protein concentrate. So looking at these in a sense, so like here where you've got the soy protein, you end up with a proper gel being formed. So again, if I try to highlight here very clearly, you see when you have the soy, you've got some as you're heating up beyond the denaturation temperature, you're actually increasing the ability of the soy to hold water. Whereas if you're looking on this other line here where you've got the caseinate, or where you have the whey protein concentrates, as you continue to look at it as a function of heating, so as the more you continue to heat, in this case it can form a gel, and when it forms the gel, but it doesn't have as good water holding capacity as you will have or binding for soy protein isolate. The other thing that it does impact on the water holding or binding capacity of proteins is the type and the concentration of salts. Well, of course, proteins are highly dependent on the type of salts. For example, if you've got a muscle proteins, and I'm going to show a little bit of this example here, which is an experiment that was carried out on different types of muscle proteins. One was from the breast and another one from thighs. And here you can see the differences between the salt concentrations, the water binding capacity, where here you see this tends to increase in percentages as the salt concentration increases. So again, this is something to think about here. You've got your muscle proteins, could be a thigh or it could be a breast, and of course the more you're carrying out an increase in the salt concentration, where you're having the salt, let's say you're having sodium chloride, where you can have the red is your you have your sodium, and then you have your chloride, you have your muscle, sorry, and then you have your sodium chloride. So what happens is the chlorides are negatively charged, the sodium is positively charged. They will interact somehow with the proteins that you have, and when you have the protein, of course, proteins can either be positively or negatively charged because they are amphiphilic, and that just means they possess both the negative and the positive charges. And so at the end of the day, depending on how many charges you have and the predominant charge that you have, this can actually end up interacting with the different ions that you've got there. If you've got a positively charged protein, which again depends on the pH, that can interact with the negatively charged part of the chloride ions. And if you've got a negatively charged protein, that can interact with the sodium. And of course, once they do, these interactions can result into formation of these networks or these interconnections, and that can again impact on the ability of that sample to hold water. This is again another example. I'll link below. I'll put the link of the publication in the link, where you can read a little bit more into details, where there's an experiment that has been done to look at the impact of salt, the type of salt, the salt concentration. And you can see here on this axis, we've got, again, if I try to highlight here on this axis, you see all the different concentrations, and of course here you've got your water holding capacity in percentage, and then you've got the centrifugation forces that were used in this experiment. On your left here you've got magnesium sulfate, and here you've got magnesium chloride, and you can see again, depending on the different salts that you have and the different concentrations of the salt, again you have quite a significant difference in the water water holding capacity. And that's something worth important again, and worth noting that if you've got, let's say, a matrix where you are trying to interact this with the salt, that will impact again on the water holding, water binding capacity. Both again, this type and the salt concentration plays an important role. As I said again, I will link that paper in the description below. When you have time or you want to understand a little bit more into that, please feel free to go and read the article. The other thing, of course, is looking at the influence of pH. I've mentioned pH already before, and you can see that looks a little bit busy, but you can see here when you have pH, of course, on this graph over here, the more you are, let's say, towards the negative pHs, it all depends on the isoelectric point of your protein. So let's say, for example, if your protein has got an isoelectric point around pH 5, that can be an example of any type of a protein. For example, if when you need to look at the type of the protein. So if you are below the pI, the protein will be positively charged, and then above the pI, the protein will be negatively charged. So when this is happening, whereby you have the differences or the changes in the charge density of the protein, so what happens is that the water binding capacity will always be the lowest at the isoelectric point, and then once you go away from the isoelectric point, the protein water binding does actually again change. So again, something you need to know is that depending on whether you've got a protein that is positively charged or negatively charged, that can actually impact on the water binding or water holding capacity. So again, if you're closer to the isoelectric point, what happens is that at the isoelectric point, the protein just basically does not have any charges, or the net charge is zero, and then the proteins does usually tend to form aggregates rather than proper gels, and those aggregates are not able to retain so much water, and as a result of that, the water binding capacity will be reduced, or the water binding capacity will definitely change. Again, that's something worth noting, how it impacts the protein. Then looking again on the issue of the water binding, or the pH here, just to show again, in that article that I've linked to the description, they've looked at the differences between the different network structures that are formed as a result of pH. Here you can see the networks that are formed. This is a very pretty transparent network that was formed far away from the isoelectric point, where the protein can either be negatively or positively charged, and of course, because of that, you end up forming what are mainly like those very fine stranded networks that you don't even see them on a confocal microscopy. But then when you use a higher resolution microscopy, like the scanning electron microscope, you see like the mesh sizes of what you have are pretty small. And because they are small, so if I try to show you here, you can see, maybe if I highlight that, again, the meshes are really very, very small. And because they are very small, what happens is that they actually function like a sponge. Try to imagine if you've got a sponge and then you soak it in water, it sucks up all the water. It doesn't become so easy to let go unless you really squeeze that very well, as compared to if you have something that is much more closer. So again, if you're looking here, when you have a more closer network, so this is a network that will be formed closer to the isoelectric point, where what happens is that the proteins are literally, the charge density is zero. They have very minimal charges on there. They tend to form like really coarse networks, and those coarse networks, they have much more, again, bigger open meshes. So you can see like the distance between there and the other one can be quite really if you try even to look at that, it's quite a bigger distance, or there's a bigger holes in there, and those holes, do actually mean if you're trying to compress or if you're trying to squeeze the network of the system, the water can easily just gush out from the system. So now, just to bring this to land, the talk today is just to show you that there are different factors that can actually impact on how the protein retains water in its systems. And so I hope that I've been able to show you a little bit of these examples. And again, I've linked a couple of other videos or other clips that you can look at to give you a little bit more insight into this topic. And hopefully this was informative. Thank you for listening.